All right, welcome to 3.3.2, the product and quotient rules. I normally start this class with a warm-up where I have people try finding f prime of x and the equation of a tangent line to this function. That's stuff we learned yesterday. I'm not going to use time on this video to do that, but it might be a good practice. So if you want to pause it and try it, go for it. Might also be something we do in our live class. All right, so we're still talking about finding shortcuts for differentiation. And one of the things I normally do is I have students try to find this. Now, there is going to be a problem with this. That times that. If I wanted to find dy dx, it's not just going to be the derivative of those separately. This would not be, let's see, derivative of that is 2x plus 0 times derivative of that is 2. That's equal to 4x. It is not that. When you have a product, you can't just find the derivative of each side separately and multiply them together. It does not work that way. It works for sums or differences. You can do it with there's a sum rule and a difference rule where you can just find them separately and add them together. That's fine. It doesn't work for products or quotients. We're going to need a new rule for that. That said, we could still find this one knowing what we know now, right? I could still find this derivative. I would just have to multiply that out first. I'd have to say, all right, well, I can multiply this out. X squared times 2x, that'd be 2x to the third. X squared times 7 would be plus 7x squared minus 10x minus 35. And then I'd say, all right, now that I've got it written that way, I can use my sum rule, which says I can take these derivatives separately. So my y prime would be 6x squared plus 14x minus 10 plus 0. Again, derivative of a constant is 0. We normally don't write that plus 0 because that seems silly, but don't forget. All right, there it is. So product rule. It is going to be really necessary because sometimes I don't want to take this step here where we multiply that out. And sometimes we can't. A problem like that would be something like this. If I said y equals x squared sine of x, that's a product. I can't somehow change that into some sum and find it that way. So we need something called the product rule. And there is a product rule. It looks like this. Don't get scared of it. It's not that bad. It says the derivative of f times g is just f times dg dx, which is the derivative of g, plus g times df of x, df dx, which is the derivative of f. So really, it's just f times derivative of g plus g times the derivative of f. All right, got it in both notations. If you prefer the f prime notation, the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. All right, that is a mnemonic device. A mnemonic device is a shortcut for remembering it. Mnemonic device, first times derivative of the second plus second times the derivative of the first. It's a good way of remembering the product rule. The product rule is definitely something you're going to have memorized. So you're going to want to memorize this big time. In fact, it's such an important thing and used so often that several people on the internet have decided to make songs to it. If you're a song person and a song helps you memorize these, I'm going to include some songs at the end of this video that you can watch just for fun and as a method to help you memorize the product rule. You definitely need to have it memorized. Pick one that you like, memorize it. Definitely get that down. All right, I've got a proof for the product rule. Normally in class, I'll actually walk through this proof. Basically, I took this limit definition of the derivative, right? Limit as h goes towards 0, and I applied it to the function f times g, which is a product, right? Went through a bunch of math, eventually got the product rule out. Wow, who would have guessed? F times g prime of x plus g times f prime of x. I'm not going to go through that now, but I would encourage you to pause this video, take a look through it, make sure it makes sense. It's a good review of that limit definition of the derivative. All right. However, right now, I'm just going to do a few examples. Make sure we have it down. This problem, remember this problem. We already found that derivative. I'm going to go up here really quick to make sure I can remember what it was. So I already know y prime is 6x squared plus 14x minus 10. But let's just find it again, except this time using the actual product rule. So product rule says you take the first, which is x squared minus 5, times the derivative of the second. Well, derivative of 2x plus 7 is just 2, plus the second, which is 2x plus 7, times the derivative of the first. Well, derivative of x squared minus 5, that's 2x. If I did it right, I should get the same answer I did up there. Let's distribute this. That'd be 2x squared minus 10 plus 4x squared plus 14x. Yep, that ends up being 6x squared plus 14x minus 10. It was a little bit more clunky using the product rule for this one. In fact, normally if I was doing calculus, I would probably not use a product rule with this one. I would probably multiply it out and then just find the derivative as normal. But a lot of the times you just don't have a choice, like this one again. I don't have a choice. If I were to find the derivative for that, I would need the product rule. There's a little FYI down here. Derivative of sine is cosine. You're going to need to know that to actually do this one. But if I had this function, y prime is not too hard to find. Y prime is just the first times the derivative of the second. I said down here, derivative of sine is cosine, so x squared times cosine of x, plus the second, which is sine of x, times the derivative of the first. Derivative of x squared is 2x. Typically, you would put the 2x in front of the sine of x, so I'd write it like that. It is technically correct if you put the 2x after it. It's just better manners and better notation to write it this way. There's your derivative. All right, that was the product rule. I'm actually going to put the songs for the product rule in right now because they seem to be a good spot for it. If you don't want songs, skip through it, but I think they can be fun. So give me just one moment. First song.
And when you want to find the derivative, you gotta use the product rule together. So how is the weather? Y prime equals u prime plus v prime u, the product rule. Y prime equals u prime plus v prime u, the product rule.
Second song.
The first times derivative of the second plus the second times derivative of the first.
All right, last one.
First D last, last D first. You must add both terms together. When our functions made up of two, the product rule.
First D last, last D first. We must add both terms together. When our functions made up of two, the product rule.
All right, that was fun, but we got to keep going. This problem is not a product. Product rule is not going to do us a whole lot of good right now. Luckily for us, there is also a quotient rule. Quotient rule looks like this. Looks complicated. Again, it's not so much. If you've got a quotient, f divided by g, you take g times df dx, derivative of f, minus f times dg dx, derivative of g, all over g squared. Right? Got it in that notation. I also have it in this notation if you prefer it. G times f prime minus f times g prime all over g squared. Same rule, just different notations. Yes, there is a mnemonic device for that. It's one I kind of like. It's low d high, so low, right, the low function, times the derivative of the high, minus high d low, so the high function is the one up high, d low, derivative of the low function, all over low squared. So there's my low squared. So low d high minus high d low all over low squared. Going to work through a couple problems like this. Again, I've got some songs that the internet likes to put up. If you want to use them to help memorize it, you're definitely going to need this quotient rule memorized. All right, so this problem, y equals x squared minus 1 all over x plus 2. If I wanted to find the derivative of this, I'm going to have to use a quotient rule. Y prime is equal to low d high. Low is x plus 2. D high means the derivative of the high one. So derivative of the numerator there would be 2x. So times 2x. Minus high d low. High is the one up top. X squared minus 1. D low, derivative of the bottom. Well, derivative of x plus 2 is just 1, right? Because it's going to be x to the 1. Bring the 1 down. That's x to the 0. So that's just 1. So times 1 all over low squared. So all over x plus 2 squared. That's it. That's my derivative. Now, yeah, we can clean this up a bit, so we probably should do that. Multiplying this through up top, that's 2x squared plus 4x. Distributing the negative would be minus x squared plus 1 all over x plus 2 squared. I can combine some like terms up here. Right, I've got some x squareds there and there. So if I combine those together, that's just a 1x squared plus 4x plus 1 all over x plus 2 quantity squared. There's my final answer. A lot of times students seem to be tempted to square this one out. They think it makes it look nicer. I'm not sure why they do. I think it actually looks nicer in factored form. In fact, that's normally something I would always just leave in factored form, because if this numerator actually factored out, maybe I could cancel some factors. It doesn't factor out in this case, so that's as far as I go. But that's how it works. So quotient rule, low d high minus high d low all over low squared. We should probably try one more to make sure we have it down. So one more time. Same thing, we're going to need the quotient rule, but this time I threw a little bit more into it. Find the equation of the line tangent to that curve at the point 1, 2. Support graphically. So if I wanted to find the equation for the line tangent to the curve, I'm going to need the derivative, because if I need a tangent line, remember that, I need a slope and a point. So for my slope, I'm going to need my y prime. So y prime, low d high. Well, low is 2x. D high, derivative of the high. Derivative of that is 2x. Minus high d low. High is x squared plus 3. Times d low, derivative of 2x is 2. All over low squared. So all over 2x, the whole thing squared, right? I square that whole low function. We can simplify this out. It's 2x times 2x is 4x squared. Minus, I can distribute that 2. So 2x squared minus 6. Do you see how I got a minus on both? Minusing both of them. Some people like making that a minus 2 in the front, so they do a negative 2 times both of them. All over, all right, 2x, the whole thing squared would be 4x squared. All right, I can combine some like terms again, right? That one and that one. That'd be 2x squared minus 6 all over 4x squared. I could leave it there. If you wanted to make it a little bit nicer, you'll notice that everything in the top and everything in the bottom, both numerator and denominator, are divisible by 2. So I could simplify it out a bit, make this, if I divide everything by 2, x squared minus 3 all over 2x squared. That's a little bit better. If it helps you out, what I just did was divided everything by 2. You can think of that as timesing everything by 1/2, multiplying everything by 1/2. Excuse my math language there. There you go. That's my derivative. However, let's make sure we answer the question. I didn't actually just want the derivative. The whole point of the derivative was so I could find my tangent line. The equation of any line requires 2 things. It requires a slope and a point. I've got the point right there, 1, 2. Derivatives tell me slopes. I want the slope when the x value is 1, so plug a 1 into there. If I plug a 1 into there, I'll get 1 squared minus 3 is a negative 2, over plugging a 1 in the denominator, 2 times 1 squared is 2, negative 2 over 2 is negative 1. All right, so then I know it's y minus y1 equals my slope times x minus the x coordinate. There is the equation of my tangent line. A lot of times students like to keep on going and make this a y equals equation, but if there's no point to it, then I'm fine. I can be done. There it is. Quotient rule. Last thing, it did say to support graphically. I'm not going to do that. When your textbook says to do that, all it basically means is graph the original function, graph your tangent line, and if you're right, you should see that it's actually a tangent line and just touches that original function at one point. You know what? I can do it. It'll only take a minute. I am going to graph that so I can support it graphically. Then I'm going to share a couple of quotient rule songs because they're fun. And then this lesson is done. You'll have an assignment. I don't have it written down here, but it'll be on Schoology. All right, here they are. My original function is in red there. My tangent line that I found is in blue here. That is the point 1, 2. It does look like it just touches my original function in one spot, and it has the same slope in that one spot. Looks like I've found it. All right, here are some quotient rule songs for you. First one.
Lodi, 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 high. Lodi, 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 high. Minus hidey, hidey, low.
Minus hidey, hidey, low.
All over low square.
All over low square.
Second one.
Lodi high minus hidey low, all over low square.
Last one.
I just use a quotient rule that goes Lodi high minus hidey low. Square the bottom and off we go. Lodi high minus hidey low. Square the bottom and off we go.
Hope you guys enjoyed it. See you later.